We also sometimes pretend that our function is quadratic so that we can apply the quadratic formula. And the reason for that is sometimes even with polynomials we get something where we can't factor, but it looks quadratic. This is a type of example that we've seen before when we were trying to factor. Here we have x squared squared minus 11x squared minus 8 equals 0. Now, that is a polynomial in x squared. It's quadratic, but we can't factor it, right? We can't come up with two numbers whose product is -8 and whose sum is -11. The biggest you could get would be -9. But we can now apply the quadratic formula. I'm going to choose the quadratic formula over completing the square here because my middle term is an odd number. But my a is 1, my b is -11, my c is -8. And so not x, but x squared here equals the opposite of -11 plus or minus the square root of -11 squared minus 4 times 1 times -8 all over 2 times 1. So that'll be 11 plus or minus the square root of 153 all over 2. Now, that gives me two possible values of x squared. X squared equals 11 minus the square root of 153 over 2, or x squared equals 11 plus the square root of 153 over 2. Now, let's take a look at decimal approximations for these numbers. If I take this and put it into my calculator, I get the decimal -0.684 approximately. And I get the decimal -0.68 approximately. Because we're working with powers higher than 2 in this equation, we're going to restrict ourselves to real numbers, which means this can't happen with x real. So there's no solution here. However, this one gives me something about positive 11.69, which is a positive number. I can take a square root of that, which means that x is just one of the square roots of this number. That's very unpleasant, right? We have a square root inside a square root. We could work on simplifying that if we felt like it. This question asks us, however, to give decimal approximations. So to do that, well, again, we just put this thing into a calculator. And we get, we'll just keep the plus or minus about 3.42. It doesn't tell me how many decimal places to round to. I'm just going to pick 2. So we got x is about 3.42 or -3.42. And in fact, we could plug in those numbers and see. We really get something close to 0 when we plug those numbers into our original equation. Again, we could have gotten up to 4 solutions. In this case, we only had 2 real solutions. Let's see another case where we pretend we have a quadratic where we don't even have a polynomial. Here we have a quadratic in x to the negative 1. We have x to the negative 1 squared plus 15 x to the negative 1 minus 3 equals 0. Now, because of that negative exponent, we have a restriction that x can't be 0. But it's pretty apparent that we're not going to get 0 anyway. Other than that, well, we can't factor this polynomial. Right? No numbers whose product is negative 3 and whose sum is 15. That's not going to happen. But if we take our a is 1, b is 15, c is negative 3, again, choosing the quadratic formula because that middle term is odd, then we get x to the negative 1 is negative 15 plus or minus the square root of 15 squared minus 4 times 1 times negative 3 all over 2 times 1, which gives us negative 15 plus or minus the square root of 237 all over 2, which means x, the negative 1 power takes the reciprocal, and it's its own inverse. 2 over negative 15 plus or minus the square root of 237. Now we'd like to simplify that, but a little bit of messing around with the calculator tells us that 237 doesn't have any perfect square factors. And we're told we don't need to rationalize the denominator, which makes us happy. Our solutions then are x equals 2 over negative 15 plus root 237, or x equals 2 over negative 15 minus root 237. Those are our two solutions. So what we've found is that just like we can pretend something is quadratic to factor, we can pretend something is quadratic in order to use the quadratic formula. It's just that there's this extra step after we apply the quadratic formula to get from whatever the quadratic formula spits out for us to the actual value of our variable.